Hello, my name is Risharin R. Chongson and I am from BSMT3P, and this is my video for our clinical chemistry. So I will, first of all, I learned a lot in our clinical chemistry subject, and one of the things that I learned in our midterms is the spectrophotometry. So what is spectrophotometry? Spectrophotometry is a absorption type of spectroscopy, which means that it measures the light that is being absorbed by a particular analyte. So we have to define first what is analyte. So analyte is anything that can be measured in the laboratory. For example, our sodium, our glucose, our creatinine. Those are examples of an analyte. So there are two types of measurement in our spectrophotometry. There is a photometric measurement and there is also a spectrophotometric measurement. In our photometric measurement, we measure the light intensity without consideration of wavelength. So on the other hand, the spectrophotometric measurement is a type of measurement of the light intensity but in a narrower wavelength, which means that it can be in the infrared, visible light, or the ultraviolet rays, or both of what I have said, or just one of what I have said. It can be just visible light only, depending on what type of light source we will be using. And we will tackle what light source is later. So first of all, the principle of our spectrophotometry is what we call the Beer-Lambert's law, or for short, the Beer's law. The Beer's law states that the concentration of the analyte is directly proportional to the optical density or the absorbance. Those two are the same, and inversely proportional to the logarithm of our transmitted light or our transmittance. Meaning that if the analyte is higher concentration, there is also more light that will be absorbed by our analyte or our substance. So when all light is absorbed, meaning there is a zero transmittance when all light is absorbed, and vice versa. Okay, so I will just enumerate what are the components of our spectrophotometer. First is the light source. This is the one that provides the energy in our the energy that could change our absorbance. This type of light is polychromatic, meaning that for example, there is all visible light is present, or infrared light and visible light is present, something like that, depending on what type of light source or what type of lamp we use. Next is the entrance slit, monochromator, and exit slit. So these three, in some reference book, it is considered as one, but these three affects the degree of the wavelength isolation. First is the entrance slit. So this entrance slit minimizes the stray light. So it prevents the scattering of our it prevents the entrance of our scattered light. That is what I'm saying pala. And next is our monochromator, which this is used to isolate our individual wavelengths from our polychromatic light. Like what I have said kanina, our polychromatic light is, for example, all visible light. So in that visible light, we just need the color yellow, something like that. Depending on what type of analyte, of course, that we will be used. And lastly, the exit slit is the one that controls the width of the light beam that will pass through. So next is our sample cell. It is also termed as cuvette or analytical cell. This is the one that holds our analyte or our solution, and that we will have to measure. And lastly is our hindi pa pala last. Our photo detector. This is the one that will power up. Tama bang term? Power up or provides more energy into the radiant energy into electrical energy. So that is the use of our photo detector. And the most common type of photo detector is our photo multiplier tube. It amplifies our radiant energy by 200 times. Yes. And lastly, our readout device. This is the one that displays our the detection, what we detect in our analyte, how many, the measurement. So in the modern, we have LED display, but in some they use like yung nagaganon. So I believe, yes, I believe I have tackled everything in the components. That will be all. Thank you for listening.